Welcome to the System Development Lifecycle Lecture. We're going to be building trustworthy systems. We have a few learning objectives. We want you to understand the system development lifecycle and its importance in cybersecurity. We want to explore how trustworthy behavior must be designed into systems from the start. We want to connect SDLC stages to concrete security measures and controls. And we want to analyze case studies of SDLC implementation in real-world scenarios. So we've learned about the CIA triad: confidentiality, integrity, and availability. So we also want to remember that security must be designed from the start and not added on. And in order to build trustworthy systems, we need security principles, methods, and frameworks that help reduce risk and maintain trust over time. Here is a general model of the system development lifecycle. We call it a lifecycle model because it spans the lifetime of a system from inception to discontinuation and disposal. There are 5 stages in this model. 1, initiation. 2, acquisition development. 3, implementation and assessment. 4, operations and maintenance. 5, sunset and disposal. The SDLC is widely used in many disciplines such as software engineering, mechanical engineering, electrical engineering, and so on. It's considered a best practice to think about cybersecurity throughout the system lifecycle to ensure that security is integrated and aligned with system functions. We know that systems are complex and they evolve, so it's easy to comprehend that we have a better chance of realizing more trustworthy systems when security is continuously considered as the system is designed, acquired and developed, implemented, operated, maintained, and disposed of. You might be wondering what activities would take place at each step in the SDLC. We don't expect you to know how to execute these activities in this course, but we realize that a more detailed explanation of activities might help you see how they can help ensure security is integrated with system functions. The first stage is initiation, where we identify stakeholders and security expectations, we define reliability and security goals, and we conduct risk analysis. This lays the foundation for building the right system with trust as a design objective, not an afterthought. The second phase is acquisition and development, where we use secure by design architecture, follow secure coding standards, and verify third-party components. And this prevents vulnerabilities from being built into the system and ensures it behaves safely and as expected under all conditions. The third stage is implementation. We conduct security testing, so penetration testing, and we validate integrations, and we train users. This ensures that system performs securely in the real world, and that users can operate it safely without introducing new risks. The next stage, operations and maintenance, we monitor performance and logs, we apply patches and updates, we respond to incidents and audit for compliance. So this maintains confidentiality, integrity, and availability over time in the face of evolving threats and operational complexity. The last stage, transition replacement, sunset disposal, is we sanitize data before retirement. We have to securely decommission hardware and ensure no lingering access or risk. So this prevents residual vulnerabilities, data leakage, or reuse of insecure components that could undermine long-term trust. So let's look at an example of how SDLC might be applied to the development of an airplane's flight management system, or an FMS. Here we see the stages and the system activities and the cybersecurity considerations in this stage. So in initiation, we want to define system purpose. So manage flight navigation, fuel, and safety. We also need to gather high-level requirements from engineers, pilots, regulators, anybody else. We want to ensure requirements address not only functionality, but also security. So that is prevent unauthorized access to flight path data. In the acquisition or development phase, we want to develop the architecture and design, including software modules such as navigation engine, autopilot integration. So we want to code and test individual components also at this stage. The considerations here, we want to integrate security into design. That is, use secure coding practices. We want to design for fail safety. We want to validate input handling and apply least privilege principles here as well. The third stage is to implement an assessment. We want to assemble components and perform integration testing. We want to ensure interaction with avionics, so the GPS, the radar. We also want to conduct scenario-based testing here. This performs security assessments and penetration testing. For cybersecurity, we want to validate against aviation, software safety, and security standards here as well. In the operations and maintenance phase, we deploy the FMS to the aircraft. We monitor performance. We apply updates as needed to weather models, navigation protocols. This allows secure update mechanisms to occur. So we want to apply digital signatures to software updates. We want to monitor for anomalies in fuel calculation, routing, or sensor data. So finally, in the disposal phase, we want to retire old FMS versions and decommission those components, and to replace with newer systems offering improved integration and reliability. We want to ensure secure decommissioning, that is, wipe onboard storage, revoke credentials at this phase. This prevents reuse of outdated and insecure systems. The system development lifecycle is used in the development of airplane systems, as we've discussed, such as the flight management system, to ensure a structured, safe, and reliable process. From initial planning and design through coding, testing, deployment, and maintenance, SDLC helps ensure the system meets regulatory standards, operates reliably, and remains secure throughout its life cycle. The flight management system example hopefully helps you conceptualize how to think about cybersecurity across the SDLC. Let's also look at a non-example or an example of what should have happened but did not. In the last lesson, we briefly looked at the Equifax data breach. Recall that hackers exploited a vulnerability in the Apache Struts framework to gain access to Equifax systems, stealing personal data of 147 million people, including social security numbers, birth dates, and addresses. Here's an analysis of the failure of Equifax to incorporate security across the system development lifecycle. So at the top, we have a table with security development lifecycle phase, security lapse at Equifax, and what should have been taken, what measures should have been taken. So in the initiation phase, cybersecurity was not prioritized as a core requirement in risk management and IT governance. If security had been established as a critical business requirement from the start, formal policies such as patch SLAs, certificate renewal protocols may have existed and then been enforced. During the acquisition and development phase, the use of Apache Struts 2, which is an open source component, they used it without rigorous supply chain security processes. While the vulnerability was in a third-party library, secure development includes evaluating and monitoring external dependencies. In the third phase of implementation and assessment, the patch for CVE 2017-5638 was not applied, despite it being publicly disclosed. The patch management and deployment are critical implementation tasks. The patch had been available for 2 months prior to the breach. Also, an expired SSL certificate prevented breach detection. Internal scans failed to flag the vulnerability, and the lack of network segmentation enabled lateral attacker movement. These failures occurred in live systems and reflect breakdowns in continuous monitoring, certificate management, and system hardening. In the operations phase, Again, the lack of network segmentation from the expired SOL certificate, delayed public disclosure and poorly coordinated breach response damaged trust and accountability. The incident response and communication plans are part of the lifecycle management and affect how organizations recover from failures. Okay, there was no disposal phase as this system has not been disposed of. At each stage of a systems development and operation, there are practical measures, methods, and tools that help control the system to assure its trustworthiness. These methods and tools that control the system might help protect it, might help detect wrong performance, might help respond in the case of wrong performance, and it might help recovery so the system is back under control. We will explore this concept of protect, detect, respond, and recover more at the end of this lesson. For now, this table helps you see that the concrete security methods and tools, aka the controls, need to appear across the system lifecycle. So in the initiation phase, again, we want to define the purpose, we want to identify stakeholders, we want to document high-level requirements. The controls then are security requirements definition and early threat modeling. In the acquisition phase, we want to design system architecture and develop and test components. The controls applied are secure coding standards, access control design, and encryption protocols. In the implementation assessment phase, we want to integrate subsystems, conduct testing, validate safety. The controls applied are penetration testing, integration testing, and configuration management. In the operations phase, we want to monitor the system in use and apply updates and respond to anomalies. So this includes patch management, log analysis, intrusion detection. And the sunset disposal phase, we want to retire the legacy components, decommission the system. This involves secure data erasure, hardware destruction, and credential revocation. So let's see this in action in a scenario, okay? You're helping to design an online voter registration system. It will allow eligible citizens to register, update their information, and check their registration status. In the design process, we have identified the information needs the system must support to function properly. So we need the information. And two, we have two security needs. The system must be addressed to be trustworthy. Okay? We also tried to think about what kinds of controls we might need and whether it's protective or detective. So as we look at these, we have an information need to accept and process registration details. So name, address, eligibility info. So the control for this would be form validation to ensure required fields are filled and data types are correct. So this would be a protective type of control. The information need number two is to allow registered users to view their registration status. So the control here would be a secure login with multi-factor authentication to verify user identity, also protective. We have a security need to prevent unauthorized users from altering voter records. The control for this would be role-based access control, or RBAC, for election officials only, also a protective control type. The final security need we've identified is to detect unauthorized access attempts or tampering. This would be audit logs with real-time alerting for unusual access patterns. This is the detective control type. At this point, we have an exercise for designing security and function that you will find in the course. At this point, you can either pause the video or you continue with the video and come back and finish the video and complete the exercise when the lecture is finished. So the next that we should look at is the benefit. So in summary, the SDLC is a structured approach for designing, developing, implementing, operating, and disposing of systems. It has several benefits for developing functional and trustworthy systems. By integrating cybersecurity activities, such as threat modeling, secure design reviews, and security testing at each phase, teams can ensure that security is not an afterthought, but a built-in requirements. So the benefits include quality assurance. So security testing, so static and dynamic code analysis, vulnerability scanning becomes part of quality control. Risk management is another benefit. Cybersecurity is a core component of risk management in SDLC. Identifying security risks early through tools like attack surface analysis or misuse case diagrams help reduce vulnerabilities before deployment, lowering the risk of costly breaches later on. Another benefit is project planning and control. When security milestones like completing a security architecture review or passing a penetration test are built into the project plan, teams maintain better control over risk, compliance, and security expectations throughout development. Yet another benefit is improved communication. SDLC encourages collaboration between developers, testers, product owners, and security teams. Cost and time efficiency is another benefit. Addressing security during early phases of SDLC can be significantly more cost-effective than fixing vulnerabilities post-deployment. Maintainability is another benefit, which secure coding standards and well-documented security controls contribute to building systems that are easier to maintain and patch. When system and software are designed with security in mind, they are less likely to require major rework, due to vulnerabilities. Finally, meeting user needs. So integrating cybersecurity into SDLC helps ensure that systems protect user data, maintain privacy, and inspire trust. Critical aspects of meeting modern user expectations. So the system development lifecycle reminds us that trust in systems doesn't come from a single feature or control. It's the result of careful, continuous decisions made throughout the system's lifetime. From early planning to final decommissioning, integrating cybersecurity into each stage ensures that systems are designed with trust in mind, not as an afterthought. When we anticipate risks early, validate system behavior regularly, and prepare for for failure as well as success, we build systems that are not just functional, but resilient and secure. In the next lessons, we'll explore how specific security controls used at the right time and place help implement this vision by protecting systems, detecting problems, responding to threats, and recovering trust when things do go wrong.